everyone. My name is Katherine Verboom, and my thesis is over the electrolytic oxidative coupling of aldehydes with alcohols to form esters. During my undergraduate career here at Georgia Southern, I worked under the mentorship of Dr. Abid Sheikh as a part of the Department of Chemistry and Biochemistry. So the first thing that people normally ask me when I talk about my thesis is why esters? Why did y'all choose esters, and what is the significance of them? Well, esters are everywhere in life and have widespread applications in the pharmacological synthesis, food, perfumes, flavors, and fine chemical synthesis. So esters are very pungent. They give off a lot of smells. They're volatile and have very great smells. They are used in the synthesis of many drugs such as aspirin, and they are used a lot to make other chemicals. So the traditional method of ester synthesis is called the Fischer esterification method, and it utilizes a carboxylic acid, an alcohol, and a bronzic acid catalyst. Our method, however, utilizes an alcohol, an aldehyde instead of that carboxylic acid, an electrolyte called tetrabutyl ammonium fluoride, or we just called it TBAF, and electricity. Another method that utilizes electricity also uses a ruthenium catalyst. Our method, however, is better because it is a catalyst-free reaction. So the structures that you see on the screen, on the top right, that is the carboxylic acid. And if you compare that to the aldehyde, which is right under the R method section, the first chemical structure on the left of the arrow, you can see that they're similar. However, the carboxylic acid already has that oxygen there as a part of the OH, but the aldehyde does not. It only has the H. And then on the very bottom left, that's just an alcohol. That's methanol, and that's pretty much like all of the alcohols that we used. To set up a reaction, you would take 20 drops of an alcohol, 20 drops of an aldehyde, 2 milliliters of acetonitrile, just so it's a solvent, and about 2 milligrams of TBAF. And all of this was added to a glass vial with a stir rod and 2 graphite electrodes. And then this was placed on the electrosyn, which is pictured to the right. That was the whole experimental setup. So for 5 hours, 10 volts of power were pushed through the electrodes, and the electrodes had the polarity switch every 5 seconds. So after 5 hours, the crude product mixture was run on a TLC against a reference of the starting material to make sure that a new product was formed. If a new product was formed, then the excess solvent was evaporated from the crude product, and then this was concentrated down. This concentrated product was then run through a silica column with a mixture of ethyl acetate and hexane, starting at 10% ethyl acetate, increasing to 20 and then 50% after every 15 tubes were collected. And every tube held about 10 milliliters, so a lot of this was collected in order to purify the product. Once the pure product was collected, it was run on proton and carbon NMRs, just to make sure that the right product was collected and that it was the product that we originally were intending to make. So a model reaction was done with 4-methoxybenzaldehyde and methanol, and this was just to see if the method worked at all. And it did. So once it was determined that the method worked, we wanted to test the generalizability of the method. So to do that, we tested different alcohols and aldehydes to make sure that it was general across them all, not just specific to 4-methoxybenzaldehyde and specific to methanol. So whenever we tested a new alcohol, 4-methoxybenzaldehyde was used as the aldehyde, and if we ever tested a new aldehyde, then methanol was used as the alcohol. So this is all of the alcohols and aldehydes that we tested, and as you can see that there are aromatic compounds, there are non-aromatic compounds, there are benzylic ones, there are allylic ones. So we tested a wide range in order to say that this is a very general method. Our proposed mechanism is that the aldehyde gets oxidized and loses 2 electrons to create a radical on the carbon. And then the electrons from the oxygen on the alcohol attack that radical. And then an oxygen with 3 bonds is unstable, so the hydrogen from the oxygen from the alcohol combines with the hydrogen from the aldehyde to produce hydrogen gas. The future work that can be done is testing other reactants other than just alcohols and other than just aldehydes. And then you can also test heterocyclic compounds to see if those would yield an ester under electrolytic conditions. I would like to thank my thesis advisor, Dr. Abid Sheikh, for guiding me through this project. I would also like to thank all of my lab mates for their continued support and camaraderie. I would like to thank the Department of Chemistry and Biochemistry and the faculty and staff that have assisted and supported me. And I would like to give my final thank you to the Georgia Southern University Honors Program for their encouragement in academic inquiry.